Hello everybody and welcome back. We're going to continue on in this video. We're going to finish up the 2010 Friar paper. So hopefully you've been enjoying things as we've gone along and you've tried all the questions. Specifically, tried question number 4 because that's the one we're going to be doing right now. Let's take a look. It's a nice little 4-part question. So, a palindrome is a positive integer that is the same when read forwards or backwards. For example, 3 palindromes are 7, 121, and 7739377. Right? They read left to right and right to left. Gives us the exact same digits in the same order. Okay. So A part, determine the number of palindromes less than 1,000. Okay. So we could have 1 digits, or 2 digits, or 3 digits. So that's going to give us a couple cases we're going to have to work out. So let's suppose we had 1 digit. Well, as an example, 7 was a palindrome. Right, we don't include, is it palindrome or palindrome? We don't include 0 in our list because we're asked for positive integers. Palindrome, okay. So with 1 digit, all 9 positive 1-digit numbers are palindromes. How about 2 digits? How many 2-digit palindromes are there? Well, they're going to look something like AA. Right? It's going to have to be the same number repeated. That way, when we read it forwards, we get AA, and when we read it backwards, we get AA. So really, it's just how many choices do we have for A? How many different values can A be? It can't be 0, otherwise we're not looking at a 2-digit number. But any of the other 9 choices for A, be it 1, 2, 3, 4, 5, 6, 7, 8, or 9, will all work. So this gives us 9 more palindromes. And now for the harder case. What if we had 3 digits? Well, they all are going to look like A, B, A. Now, A and B could be the same. But the point is, we're not assuming that B is the same as A. We're not assuming that it's just 1, 1, 1, 2, 2, 2. We could have 2, 3, 2. The example they give is 1, 2, 1. That's definitely got a different middle number. Once again, A can't be 0. So we have 9 choices for A. Now B can be 0. Right, the middle number can be 0. That would still leave us with a 3-digit number. 101 is still a palindrome. And that's all the cases. We have 1 digit, 2 digits, or 3 digits. So 9 in the first case, 9 in the second case, 90 in the next case. So that gives us 108 palindromes less than 1,000. And we were asked for 1,000. Let's just double check. Otherwise, we'll have more cases to do, like 4 digits and 5 digits. Nope, less than 1,000. Okay, so that's A part. Got us accustomed to palindromes and counting them. So B, determine the number of palindromes with 7 digits. Okay, so we know what they look like when it's 2 digits. It looks like AA. 3 digits, it looks like ABA. 4 digits should look like ABBA, which is the name of a nice band. So that's 7 digits. And I have A, B, C, D, C, B, A. That's what a 7-digit palindrome is going to look like. And we know that A can't be 0, but B, C, and D certainly can. And any of the other digits will suffice. Right, so we can have 1, 0, 1, 2, 101, for example, something like that. Now our choices of A, B, C, and D, they're all independent of each other. All we really need to do is make sure that A isn't 0. So we have 9 choices for A, 10 choices for B, 10 choices for C, and finally 10 choices for D. And that gives us 9,000 7-digit palindromes, and that's what we're asked for, the number. Okay. So that's A and B. We've been just counting a lot of palindromes, but I would expect it to get a little harder, maybe throw a wrinkle in there in terms of counting things. So C part. If the palindromes in part B, so the 7-digit ones, are written in increasing order, determine the 2,125th palindrome on the list. Okay. So we're writing them in increasing order. So really that first digit, that A digit, is going to help us determine the order. Remember, we order numbers by the biggest number we see first. So what can A start off with? What can we start the list off with? So we got 1, B, C, D, B, C, B, C, B, 1. So we get 1,000 palindromes of this form. And that's all the palindromes that start with 1. And they're automatically less than all the palindromes that start with 2, all the ones that start with 3, all the ones that start with 4. Right? Any 7-digit number starting with 1 is automatically less than any 7-digit number starting with 3. I don't care what else they look like. So we've got 2,000 that are less than the number we're looking for. We're looking for 2125. Right? So There are 1,000 that look like 3BCDBCB3. The pen is not cooperating a little bit. Or maybe I'm just writing a bit too fast. So let's clean up our notes for just a second. So, including all the ones that start with 3 give us the 3,000 smallest. All these ones are still bigger than the ones starting with 1 or starting with 2, but now we have the 3,000 smallest. So what we've narrowed it down to is it's got to be in amongst this 1,000. Before we had 1,000 that started with 1, 1,000 that started with 2, so those were the 2,000 smallest. But if we were to start looking at things that start with 4, there'd be at least 3,000 that are smaller than it. We want the 2,125th from the bottom. So this is what our palindrome looks like. We don't know what the rest of it is, but we do know this is what our palindrome looks like. Now B can at worst be 0. So let's just stop and explain a bit more of what we're doing. So any palindrome of the form 31CD C13 has 2,100 Right? Just explaining it a bit more. Here's a group of 100. Here's another group of 100. So anything of this form has to be bigger than this group and the couple thousands we saw before it. So these guys are going to be bigger than at least 2,200. So we've gone too far again. Our palindrome has to look like this. C13. So we're closing in ever so slowly. So the next thing that determines our order is C. So there are 10 palindromes of the form 310D013. Right? What do we want? We want 20. Okay? There are 10 of the form 311D113. Okay. So these guys are bigger than at least 2,100. These are bigger than at least 2110. Bigger than at least 2120. Bigger than at least 2130 palindromes. So the one we're looking for is going to look like 312D213. Okay. Now the lowest D can be is 0. And actually we can write out our candidate. So this one here, he's going to be 2,120th, I believe. This is 2121st. Let's just double check that we have the numbering right. We don't want to be off by one. That would just be awful. No pun intended. So this guy automatically is bigger than 2100. So if I just put a 0 in here, that's the very minimum he could be. So he's definitely bigger than 2100. So this one, if I put a 0 in here, he's automatically bigger than at least 2120 of them. But he's no bigger than any of the others. So he's got to be the 2120. Okay, so we're definitely on the right track. Alright, one more to go, I think. Or actually, one, 2, 4213 is 2,124th, and 3125 I think this should be the right answer, but now I'm thinking back to what I saw before. So 1BCDCB1 is automatically bigger than 0 of them. That doesn't make it the 0th palindrome, so we're off by 1. So in actuality, this one here is the 2,121st, 22nd, 23rd, 24th, and this one is the one we seek. Right? Yeah, I think so. I'm pretty sure. So, let's get out the black pen. So 3124213. This is 2,125th. Palindrome. And that's what we were asked for. I'm pretty sure I now have the ordering right. If I'm off, I am off by at most one. You can read their solutions if you want, but I'm fairly certain I'm correct. And hopefully, if you've tried the problem, which you should have, hopefully you and I got the same number. If you got one off, you might be right. And so go to the official answers. You're always welcome to do that. You can find them at the past contest link that I'm going to post below. Alright, so that was C part. Now D. Determine the number of 6-digit palindromes that are divisible by 91. Okay. So it's a little different. C we were ordering, and that was tricky enough. I'd say C so far is the hardest part of this problem. D is back to sort of determine a number, so it's going to be back to just sort of counting and combinatorics a little bit. Okay, so 6-digit palindromes. Well, what do those look like? So A, B, C, C, B, A. So we have duplicates of letters in each place. Okay, once again we have 0 is less than or equal to B or C. And 1 is less than or equal to A, which is less than or equal to 9. A can't be 0. So that's probably an important fact here. Now 91 is 7 times 13. So, usually when you do a question like this, like how many are divisible by 6, you would say, okay, well I know the divisibility rule for 6. You have to be divisible by 2 and by 3. Well, what does divisible by 2 mean? You have to end in an even number. And divisible by 3, the sum of your digits must be a multiple of 3. But 91 doesn't have as clear-cut a divisibility rule. It has a rule, but it's not a very good one. It doesn't speed anything up. And it's not well known. So I think we should probably shy away from the divisibility rule for 91. Same with divisibility rules for 7 and 13. They're also not very useful, I don't think, in this situation. How about we take a look, because the B's there look like 1001. And I'm pretty sure 1001 is divisible by 91. I think that's why they chose it. So, if you'll indulge me for a moment, let's experiment a little bit. A, B, C, C, B, A. Well, that's A, which is something from 1 to 9 times 100001. And then B times 10010. I'm pretty sure this number here is divisible by 91. Plus C times 1100. Okay. Now, I've been saying pretty sure, but let's actually just check. 10010 divisible by 91. So for A, B, C, C, B, A to be divisible by 91, we need 91 to be divisible by what's left over here. A times 10001 plus C times 1100. Now, I don't think either of those other two are divisible by 99 or 91, but let's double check. So 1100. Is he divisible by 91? No. Is he divisible by either 7 or 11, the prime factors? Not divisible by 7, not divisible by 11. Just quick divisible by 13. So quick calculator check shows that 91 doesn't divide 1100, neither does either of the factors, 7 or 13. How about 100,001? Is that divisible by 91? No. Is it divisible by 7? Nope. How about 13? No. Okay. So none of these factors work, because if, for example, 1100 were divisible by 13, to make it divisible by 91, we just need C to always be a multiple of 7. So, unlike the thing with B, which we could take out, it's automatically divisible by 91, no matter what B is. A and C will probably have to be very special values. So, sorry, either A equals C, A is less than C, or A is greater than C. Okay? Now, the reason I'm doing that is because one of the other things I figured out while I was calculating whether or not these things are divisible by 91, I had a hunch, and 101101 is a multiple of 1001, which is a multiple of 91. So if A is equal to C, then we get A times 101101. We get a multiple of 91. So what is that? That's the A equals C case. Right? So we know that A0AA0A is divisible by 91. So we can take a difference of C and A. We'll be left with, we can sort of break this, what's left over. Remember, we can ignore the B's. So we can take what's left over, get rid of the A's. That's divisible by 91. So we need 91 to divide C times A, and 1100. And that can't be done. 1100 is not divisible by 7 or 13 or 91. That gives us no palindromes with A less than C. Right? We can't have 91 divide this. 91 is 7 times 13, so we would need 7 to divide this and 13. Now, being primes and not being factors of 1100 would mean that we would need 7 to divide C minus A and 13 to divide C minus A, and that can't happen. C minus A, that's single digits subtracted off of each other. It doesn't work that way. How about if A greater than C? I don't expect this to work, but AOCCOA, well, that's going to be C times 101101, which is fine. That's a multiple of 91. And A minus C 10001. So what do we need? We need 91 to divide A minus C times 10001. So that's true only if 7 divides this, and 13 divides this. Let's clean that up a little bit. Now, neither 7 nor 13 divide 10001, as we verified earlier, but we can check again on our calculator if we're a little unsure. So being primes, we need 7 to divide a minus c and 13 to divide a minus c. But it can't happen. So what I've done when I said can't be done, I've written out a specific example just in case they are looking for this reasoning. So the only condition we need is a equals c. B can be whatever we want. We took b out quite a while ago. So we were asked to count the total number. Well, there are 10 choices for b. And 9 choices for our little pair that are coupled together. A equals c. Remember, c could be 10 different things. But a can only be from 1 to 9, and c has to be equal to a, so whatever we choose for a, whatever of the 9 choices for a we have, c has to match. So this gives us 96-digit palindromes. That are divisible by 91. And I believe that's all we were asked for. Let's just double check. D part, determine the number of 6-digit palindromes that are divisible by 91. Well, we did that. We figured it out. 90. We weren't asked to list them, and that would be a hell of a list to make anyway. And that concludes the 2010 Friar. So hopefully you guys have enjoyed everything, and I'll see you guys in some other video at another time. So thank you so much for watching.